In section 3.4, we're going to spend a little bit of time talking about a really crucial concept in all of calculus, which is the concept of differentiability. Now, this was a concept that back in Calc 1 was discussed very heavily, and as we've seen throughout this section so far, we're going to build our intuitions of how this terminology is going to be used in Calc 3 based on how it was used back in Calc 1. Okay, so let's take a look here at this opening motivation. Recall that back in Calc 1, we said that a function was going to be differentiable at a value of x if it was simply just the case that f prime of x existed. That is, if I actually had a tangent line on the curve that I could find the slope of at a particular x value. Now, what was kind of interesting, again, about this value existing is that it implied several different things about the function. First off, if my function was going to be differentiable, so let's pretend I have maybe a function that looks like this, and I'm going to imagine maybe I'm dealing with a point here of x0. If my function was differentiable, what that meant is that at the point on the curve when x was equal to x0, there had to be a tangent line that was non-vertical. So that way I could again actually find its slope. It also then had to be the case that because the line was a tangent line, you can even see here in the picture, it must have been the case that at least when I stay pretty close to this initial point of contact with the curve, that my blue tangent line is almost going to be the same as the black curve around it. In this picture, you can kind of see that happening like over here on the right side, where my blue tangent line is almost lining up with my curve perfectly. Of course, the further away I get from x0, the more of a break and a separation I see between the blue tangent line and the black curve. But again, as long as I stay near x0, the function can be approximated by that linear function. And finally, we had an important idea that differentiability implied continuity. That is, if a function was differentiable at a point, it had to be continuous there. There couldn't be any holes or breaks or jumps or gaps at that point if I was going to have a differentiable function. So in Calc 3, we want to go ahead and try to expand all three of these notions, all three of these kind of implications of differentiability to our 3D surfaces. So let's take a look. We want to extend this notion of differentiability for functions with 2 or even 3 variables. We'll focus for the moment on functions with 2 variables. So, what is it that I need to have? Let's take a look down here. Let's suppose that I have some sort of a surface. Okay? If I wanted to know if this surface is going to be differentiable, say like at this point that I have down here, if I wanted to know if the surface was differentiable there, what I would need to be able to have is some sort of a derivative or derivative-like thing existing. I'm not quite sure what the rigorous definition should be just yet, but I wanted to at least imply the same three sorts of things. I want to be able to say that instead of a tangent line at that point, I should be able to construct a full tangent plane. And that tangent plane should have a slope, quote unquote, in a way that makes it non-vertical, right? So there should be some tilt to this plane, so it's not perfectly straight up and down. It should then also be the case that this plane does a decent job of approximating the surface near that point of tangency. And you could kind of get that idea from taking a look at this picture, right? Like if this pink plane that I have here actually touches the surface at this point, then as long as I stay really close to that point, you should hardly be able to tell a difference between that surface and the actual plane itself. Maybe in like some small window around that point, it's pretty darn close to being identical to the surface. And finally, what we'd like to have be true for whatever definition we come up with for differentiability, we want it to be the case that if my function is differentiable at a point, it will be continuous at that point. Okay, so what would be the definition that could possibly work? Well, very strangely, we get this definition. A function of 2 variables is said to be differentiable at a point, provided that, notice here, I have 2 different derivatives that exist. That is, my partial derivative with respect to x needs to exist at that point, and my partial derivative with respect to y needs to exist at that point. And I need to have this absolutely horrifying limit exist and specifically come out equal to 0. Okay. Um, I include this limit in here really just for the shock factor of it. We're never going to be dealing with differentiability of a surface by calculating or dealing with this limit really at all. Okay. This is the actual or a part of the actual definition for differentiability, but instead we're going to in our class be taking a more intuitive approach. We're going to again be looking at surfaces and trying to understand if these three conditions appear to be applying to it. And that's kind of what I state down here. Intuitively, again, all of this means that when I create a tangent plane or a linearization of my surface at a point AB, the tangent plane does a good job of approximating what the surface is going to look like. Okay. So when we think about differentiability, we want to think about the concept right now of the curve, or the surface, I should say, having this tangent plane that does this good approximating, and the surface itself being continuous, or that is kind of being connected, being not having any holes or breaks or jumps or gaps. Okay. The idea, though, of this particular definition does continue to extend to larger and larger spaces, so we could deal with functions that have more and more inputs. And does relate, as I state down here in the second note, to some other things that we'll see later in the class.